In this video, we're going to look at Newton's law of cooling, another application of first order differential equation. So, Newton's law of cooling states that the rate of cooling of an object is proportional to the temperature difference between the object and its surrounding, provided that this difference is not too large. So, the difference between the temperatures is not too large, then Newton's law of cooling holds. Now, if we let T of T be the temperature of the object at what? A time, and Ts, which is Ts, be the temperature of the surrounding, then we can formulate Newton's law of cooling as a differential equation of the big T over the small t is equal to Kt minus Ts. So this is Newton's law of cooling when we formulate it with using differential equation. So where K is the constant of proportionality, and we could do this, we could see we can reduce the using separation of variables. That's separable differential equation. When you use that, let's try and do that. So we're using separable differential equation. We will know that we are grouping, so we are going to have the big T all over T minus Ts is equal to K dt. Then we integrate both sides, right? So when you integrate this, when you integrate this, when you integrate, you're going to get ln bracket to be T minus what? Dx is equal to, this will give you Kt, and there will be a constant plus C. So now we have a constant here, which represents what? From growth and decay. We know that that one becomes the initial constant, right? And which is the arbitral constant. Then we can therefore find, making big T the subject here, we can find E exponent, that's elimination, that's E ln T minus what? Ts is equal to E Kt plus C. So this will cancel this. We're going to have our T minus Ts is equal to what? Kt times E exponent C. And we know that E exponent C1 is the same as a constant. So T minus Ts is equal to what? Ekt times C. So at the end, we are going to have our Newton's law of cooling to be E is equal to Cekt plus Ts, whereby this becomes the surrounding temperature, and the T becomes the temperature of the object, which is the temperature of the object. This becomes the initial value, and the K becomes the other information, that's additional information constant. Yeah. So this is the formula for the Newton's law using separable method. So we had it here, and then due to separable method, we separated it and had this. That's an application of first order differential equation. So the constant of integration C can be calculated by using initial condition, and the constant of proportionality K can be calculated by using additional condition. This is very important. If you've seen through from the growth and decay to the Newton's law of cooling, we have initial condition and additional condition. The initial is for the C, so C is for what? Initial condition. So always we use the initial condition from the C, and the K is the what? Additional condition from the question. So let's take an example and let's see how we can solve this. With the example, a glass of hot water has an initial temperature of 80 degrees, placed in a room where the temperature is 30 degrees Celsius. After 1 minute, the water temperature dropped to 70 degrees Celsius. What will be the temperature after 3 minutes? And at what time the water cools down to 40 degrees? So for this question, we have to use Newton's law of cooling, which is given by the formula dt over dt is equal to K T minus Ts. And when you use differential equation to reduce it, you're going to get T is equal to Tx plus CEKT. So let's do something. Also, we have the initial condition, which is T naught is equal to what? The initial condition was 80 degrees. And the temperature of the surrounding, Ts, the temperature of the surrounding, the room is what? 30 degrees. And the additional condition, did they give us any additional condition? After 1 minute, the water temperature drops to 70 degrees. So additional condition was also given, which is T 1 minute is equal to what? 70 degrees. So therefore, let's start the question. So now we can know that we're finding, so from here, we can try finding our initial value, which is C. So therefore, we have our T is equal to Tx plus CEKT, which is equal to the initial condition, which is T naught, because the C, we find the C is the initial condition, which is equal to 30 plus CE naught, because at initial condition, T becomes 0. Let's note that. And therefore, we have our initial condition for the T to be 80, which is 80 degrees. We are going to have our 80 is equal to 30 plus CE naught. And this becomes, this CE naught is 1. So therefore, our C becomes 80 minus 30, which is equal to 50. So therefore, we have our C to be 50. So we'll do some substitution, right? Let's do some substitution. Then, so therefore, when you come into the equation, you're going to get our T is equal to Ts plus 50 EKT. And then we know that our Ts surrounding is what? 30 degrees. So we're going to have our T is equal to 30 plus 50 EKT. Now, what you're supposed to find now is the additional condition, which is the constant, additional condition constant, which is the K. So therefore, we need to use the additional condition constant to find the K. Now, they have some additional condition, which is at 1 minute, the temperature is what? 70 degrees. So then we need to use that one. Let me shift it here small. Therefore, after 1 minute, that means that T1 is equal to 70 degrees. So therefore, we do some substitution here. So we have our T is equal to 30 plus 50 ECKT. And now we have this initial condition. So that will be 70. 70. We are using the initial condition now, T1. 70 is equal to 30 plus 50 E. This is going to give you a K because it's 1 minute. We are using 1 minute. So these are additional information. Then we can find our K. Therefore, we try doing substitution. So we are going to get that EK is equal to what? This is going to give you 40 over 50. And therefore, we find the length of it. So when you find length, EK is equal to length 40 over 50. And this will cancel this, giving you our K is equal to what? Length 0. So we have our key. So this is our key. So this is very simple. There are two things. We are finding the initial condition to find the initial value, which is what? A C. And then we use the additional information to find out our key, which is what? The additional value. Are you getting it? Yes. So now after finding our key, we can move on and find the question was asking us to find what will be the temperature at after what? 3 minutes. So we are finding T after 3 minutes. So T3. So that will be very simple as that. Let's go and see. Let's go down small. So we are finding what will be the temperature after 3 minutes. So that means we are finding. So therefore, we can put this equation that T, which is equal to time, is equal to what? 30 plus 50. We now know K is what? We had our K to be what? Length 0.8. Then our T. So therefore, we're finding at 3 minutes, what will be the temperature? I'm going to have this one will be 30 plus 50 e ln 0.8, and that will be times the time, which is what, 3 minutes, so times 3, because at T3. So therefore we solve this. When you solve this correctly, you're going to get the temperature to be 30 plus 25.6, which will give you 55.6 degrees. Very simple as that. And they are asking us also to find at what time the water cools down to 40 degrees. So you are finding at what time. So we now know T is equal to what? 30 plus 50 EKT. And you are finding time, right? So now they gave us 40 degrees. So 40 is equal to 30 plus 50 E ln. And we have 0.8 times our T. I getting it? And when we do that correctly, we are finding our T. When you do that correctly, you need to find exponent of this. So you send this one here. So then you're going to get E ln 0.8 T is equal to 10 over what? 50. And then to find the ln of both sides to cancel out, then you're going to get our T should equal to what? Ln 0.2 over ln 0.8, which will give you 7.2 minutes.